So what is a force? As we talked about before, a force is just a push or a pull, but of course an object has to be involved. So the force acts on an object, and a force describes the interaction between two objects or an object and its surrounding environment. Every force has an agent, something that acts or pushes or pulls. So let's look at a spring force. A compressed spring, which means at this point, the spring is in equilibrium, it's at rest. But if I were to push this object in this direction, so I compress the spring automatically wants to return to its state of equilibrium. So the force of the spring is going to push in the opposite direction, which is why you have an arrow to the right and F sub SP for force of the spring. Now, if you take the same spring from its state of equilibrium and you pull it in this direction, the spring is going to want to return to its state of equilibrium. So the force of the spring is going to pull that object back until it reaches its point of equilibrium, which is why your force arrow is in the leftward direction, F sub SP. Now, springs come in many forms, so when deflected, they push or pull with a spring force. So there are 5 basic types of forces. You have a normal force. And how would you denote a normal force? Well, you can write F for force, sub N for normal. Then you have what's called a contact force, friction force, and generally, as we get further into frictional forces, you'll see that it can be either F sub K for kinetic force, or F sub S for static force, or static friction, or kinetic friction, or you can just put a sub F for friction. Then you have weight, which can be noted with a W. Then finally, tension, which can be denoted as F sub T. And we'll see a table later in the presentation where you will have all of these listed. They're listed a little differently, but if you know the basic ways to list them, you'll be fine. So let's look at the normal force. As you see in the image, it appears as if the person is moving leftward, but that's just because there are clouds in the background that are moving rightward. So basically the motion is just up and down, up and down. So the normal force is a perpendicular force. The image shows a normal force pushing up on the books. If there was just one book, or the stack of books, if there was a stack of books sitting on a table, then the normal force would be pushing up the book from the table. The normal force is denoted by a lowercase n with an arrow over it to show that it is a vector. So again, here's a picture of your textbook sitting on a table. This arrow shows the direction of the normal force, and it's perpendicular and it's pushing up. So here's a figure 4.9 video that shows an atomic model of the force exerted by the table. And then there's another video for you to look at what is physics, or what the physics pushing down to move upward. Watch those videos and return to the presentation, please. The next force. Well, the next force is a contact force, and you can pretty much look at the image of the Giphy and determine what a contact force is. It's direct contact between two objects, the cat's paw and the little cardboard, I don't know what that's called, that thingy that was put in the garbage can. Okay, the cat is really having a ball with that. But when his paw comes into contact with that cardboard, that is a contact force. Let's look at friction force. Now we saw with the normal force, the normal force is perpendicular to the object. A parallel force exerted by a surface on an object gives you friction, and it's denoted by a letter F if it's not specifying kinetic or static friction, or it can be F sub S for static or F sub K. Now, what is the parallel force on the surface of an object? Well, as our slider comes in and he's moving towards the right, friction is moving in the opposite direction, which is causing him. So the friction from the ice is actually, in this slide, the sled is moving to the right, but it's slowing down. So as you see, F sub K shows kinetic friction, and it's moving in the opposite direction of the sled. Whereas F sub S means she's pulling on this big box, but she can't get it to move. So the box is experiencing static friction because it's not moving. But if she were to pull very, very hard and keep pulling, and she got it to move a little bit, that point where it starts to move is called maximum static friction. Either way, you'll see the direction of the sled is to the right, so kinetic friction is to the left. The direction of the box, well, it's just sitting there at rest, but she's pulling to the left. But the friction is so strong to the right that it's not moving. Let's look at weight. The pull of gravity on an object. Weight equals mass times gravity. Okay, it's denoted by lowercase w with an arrow over it because it's a vector. So when you go out of space or out of the troposphere or the tropopause, the stratosphere, etc., out of our universe to the moon or to Mars, to Jupiter, you weigh less because there's less gravity than there is on Earth. Okay? So your mass times your gravity will give you your weight. So this little guy, he keeps trying to pull himself up on top of the desk, but basically his weight is overcoming his goal. His mass times gravity, which is pulling him back down, is a little bit larger than the strength of the force in his arms. So with weight, if we throw this ball upward, weight is down. If we throw this ball down, the weight is still down. If this ball is in projectile motion, the weight is down. If the ball is rolling on the floor, the weight is down. If it's just sitting there at rest, the weight is down. So what does that mean? An object's weight vector always points vertically downward, no matter how the object is moving. So our next force, tension force. As she grabs that bar, you notice that it has two ropes or cords attached to the bar in an upward direction, okay, keeping her up in the air. So when a cord, rope, string, chain, thread, etc. is attached to an object and it's pulled, the force applied to the object is tension. So tension is applied to our acrobatist, and that's the force that is applied. Tension force. The rope exerts a tension force on the sled. Okay, so you'll see the arrow. The dot represents our object, which is the sled. The arrow to the right and upward represents the direction and the magnitude of the tension force. So when a string or a rope or a wire pulls on an object, it exerts a contact force that we call the tension force. The direction of the tension force is always in the direction of the string or the rope. Examples of force vectors, tension, and weight. So all the tails of the vectors are placed on the particle that represents the object, regardless of where the force is applied. So this is the object. So wherever that force is going, it doesn't matter. The tail of the vector will be here. So she could be standing over here and pulling on the rope. If that were the case, then the arrow will be moving in this direction. But what's important to know is that the particle, the dot, represents the object. Here, to the right, the dot represents the box at rest. And the direction of the force is in the direction of gravity. Let's look at measuring force. So basically the magnitude, or how large or how small a force is basically determined by how strongly an object is pushed or pulled. The unit of force is a Newton, named after Sir Isaac Newton, the physicist who discovered these laws of motion. And 1 Newton equals 1 kilogram times meters per second squared. And if you notice, meters per second squared is acceleration, kilogram is mass, Newton is force. Force equals mass times acceleration. Is the same as weight equals mass times gravity. So if we were to state this in words, the force required to accelerate an object with a mass of 1 kilogram, 1 meter per second. So basically all that's saying is that your speed increases by 1 millimeter per second after every second. So basically your velocity changes every second. That's all they're saying that 1 Newton is. That's your velocity changing every second. An arrow points in the direction of the force, and the length represents the magnitude of the force. Superposition of forces. Basically, we're looking at the resultant force. So when two forces act at the same time on the point of an object, the effect is the same as a single force, equal to the vector sum of the original forces. A resultant. So a resultant equals force 1 plus force 2 plus force 3. So basically, force 1, force 2, force 3. It's the sum of all those forces, and that will give you basically your resultant. And if you remember, these are your component vectors. Now, if you notice, the component vectors are F12, or F sub 1, 2, and F sub 1, 3. Remember, if it's in the x direction, to find that component vector, you have to take the product of F cosine theta, and to find it in the y direction, you have to find the product of F sine theta. Same concept you'll see over and over again. If an object doesn't have any forces on it whatsoever, or if you had an object that had a lot of forces but they canceled out, then the vector sum altogether is 0. And there's a 0 resultant force, and that equals no force. And that means that object is simply at equilibrium. So Newton's first law, the fact that an object at rest stays in rest unless an external force is applied, or an object in motion stays in motion unless an external force is applied, that's known as the law of inertia. It's an object's resistance to the change in velocity. And if you remember from high school chemistry class, mass is anything that has matter and takes up space. So this measures how difficult it is to change velocity, start an object moving from rest, or change the direction of an object. Let's look at our first problem. The average human has a force of approximately 700 newtons. What is this in pounds? Remember, W equals M times G, and 1 Newton equals 1 kilogram meter per second squared. Okay, so first thing we want to do is change from newtons to kilograms. So you have 700 newtons. All right, that's your weight, equals, what is your mass? Well, we don't know it, so we're just going to put kilograms here. And then we know that G is 9.8 meters per second squared. All right, so rearrange your equation to solve for kilograms. It's going to be 700 divided by 9.8, and you should end up with 71.4 kilograms. So now that you have your answer in kilograms, the question asks, what is this in pounds? So now you're going to convert kilograms to pounds, and here is that conversion factor. So you have 71.4 kilograms equals, well, now we put in our conversion factor, and we want kilograms in the denominator because we want the kilograms to cancel, so we end up with pounds. So I'm going to put 1 kilogram in the denominator, and I'm going to put 2.21 pounds in the numerator. Okay? So now, multiply across. Let's see, kilograms cancel. Should be times, sorry. Kilograms cancel. So you multiply 71.4 times 2.21, then you divide it by 1. And your answer should be 158 pounds. So again, here are the common forces and their notations. Their notations may be a little different. So when you see tension, that's basically F sub T. Normal force, F sub N. Static friction, F sub S. Kinetic friction, F sub K. Got weight, which can be F sub W. Spring force, F sub SP. So whatever you're comfortable with, that's fine. Just make sure you know what you are referring to. Now we'll work on some free body diagrams. This is a way to get you to clearly understand how forces are applied to objects. So number one, a girl is suspended motionless from the ceiling by 2 ropes. Diagram the forces acting on the combination of the girl and the bar. So I'm going to use, for an object, I'm just going to use a little box. So the box is the girl. Okay, so she's suspended motionless from the ceiling by 2 ropes. So we've got 2 ropes going up. Diagram the forces acting on the combination of the girl and the bar. What's missing? Well, she's hanging down, so force of gravity is acting downward. Okay, so gravity is pulling on the girl. I wouldn't mark it wrong if you said the force of weight. Okay, so 2 ropes up, tension forces. So we're going to label those. And I'm going to put G here for gravity. Number 2, a flying squirrel is gliding from a tree to the ground at constant velocity. It says to consider air resistance. So we're going to diagram the forces acting on the squirrel. So this box is the squirrel. We're considering the air resistance. Okay, so air, if the squirrel is coming down, then the air is a force that's moving upward. So let's put force of air. And then gravity is pulling that squirrel downward. Okay? Next, a rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces, neglect air resistance, diagram the forces acting on the book. Okay, so let's draw our book over here. All right, number 3. For number 3, it says, I'm sorry. Yeah, we're at number 3. A rightward force is applied to a book in order to move it across the desk with a rightward acceleration. So, we're applying a force, an acceleration to the right. There's a book, and it's sitting on a desk. So you know already that there's going to be a normal force in the upward direction. And opposite to that normal force is gravity. And then, but we're missing one more force. What is that? The book is moving to the right on the desk. And it says, consider frictional forces. So if the book is moving to the right, there's a parallel force on the surface of that desk that's moving this direction. And that's your frictional force. This is your applied force. Same idea with number 4. Same idea with number 5. You can work on those. I'll go through, let's see. I'll go through the last 2 with you. A football is moving upwards towards its peak after having been booted by the punter. Neglect air resistance. Diagram the forces acting upon the football as it rises upwards towards its peak. This is the trick part of the question. It says diagram the forces acting on the football as it rises upward towards its peak. So basically, for number 8, if this is your football and it's rising upward, the only force acting on that is gravity, because it's in free fall. And gravity is the only force that's active in free fall. Now let's look at the last one. A car is coasting to the right and slowing down. Car is coasting to the right and slowing down. Neglect air resistance. Diagram the forces acting upon the car. So here's our car. We have a normal force going up. We have gravity coming down. It's slowing down. It's coasting to the right and it's slowing down, which means you have friction to the left. Okay, so let me see if I can draw that a little bit. Okay, so you have gravity, you have your normal force, and you have your friction. That's it. Drag and thrust. What is drag? Air resistance is basically a significant force on falling leaves. So as you watch a leaf falling from a tree, you'll see that it kind of falls slowly. It may move a different direction. That's because the different molecules in the air are pushing upward on that leaf. So drag basically is kind of like friction, and it's moving in the opposite direction that the object is moving in. And that's basically drag. It's the resistive force of fluid, and we know that fluid can be either a gas or air or water or any other kind of liquid. Anything that flows on a moving object, excuse me, is called drag. So like kinetic friction, drag points opposite direction of motion. So you can neglect air resistance in all problems unless a problem specifically tells you do not neglect air resistance. Then we have thrust. Thrust usually deals with airplanes and rockets. It's a force that occurs when a jet or a rocket engine expels gas molecules at a high speed. That gives it its ability to thrust upward quickly. So thrust is a force that's opposite the direction in which the exhaust gas is expelled. So down here you see the exhaust gas, it's going downward because it's expelled, and the thrust is pushing that rocket upward quickly. That's thrust.